Good morning. Welcome to your astronomy unit. This is the unit you guys have been waiting for, I know. So first we're going to start with your astronomy vocab. So if I'm looking at an axis, my axis is my imaginary line that connects from one pole to the next pole. For us here on Earth, connects the North Pole to the South Pole. Rotation is that spinning of an object on its axis. So if I take the globe and I spin it, alright, it is rotating. My axis is that line, actually it's a rod that connects from the North Pole down through the South Pole for the globe. Revolution is when one object moves around another object. For instance, I have my Earth. My plastic cup is revolving. It's moving around the globe. All right? Rotation, it's spinning on its axis. Revolution, you have one object going around another object. Celestial sphere is my imaginary sphere that encircles the Earth. Anything that you find in your celestial sphere is a celestial body. Be it a moon, be it a sun, be it a planet, be it a star, or be it a man-made satellite. They're all celestial bodies. Zenith. If you go outside during the night and you stand and you look straight up, so right above your head, anything that is directly above your head is your zenith. The horizon is where the land or the water meets the sky. Altitude, you're looking at the number of degrees or the angle from the horizon to your object. So we're going to look at a couple terms. Aphelion. Aphelion is when the Earth is the furthest from the sun, and believe it or not, it's July 4th. Perihelion is when the Earth is closest to the sun, and that's January 4th. The reason we have summer in July, even though we're further away, it has to do with the tilt of the Earth, which we'll talk about later on. The next one, apogee, is when the moon is furthest from the Earth, so it appears smaller. Perigee is when the moon is closest to the Earth, so it appears larger. Geocentric is, if you break it down, geo meaning earth, centric, center. So the belief that the Earth was the center of the solar system and the sun, the moon, and all the planets revolved around it. Heliocentric is what we believe now. The sun is the center of the solar system. The planets revolve around the sun. Retrograde. When an object appears to be going backwards, but it's actually just slowing down. You're on Route 81. There's a car traveling right next to you, going the same speed. They slow down. To you in your car, it looks like that car is going backwards, but actually all they've done is slow down. Constellation. Now, constellations you guys have been looking at every time you walked into this room, because in the alcove you had constellations. So they're groups of stars that form an image, be it a person, be it a place, or an object. Circumpolar constellations. They're the constellations that we see all year. So for us, if you look at it, anything like the Big Dipper, we see the Big Dipper all year. we see the Little Dipper all year. They're circumpolar constellations. Seasonal constellations we only see in certain times of the year. They're not visible all year round. Solar noon. Solar noon is the time of the day that the sun is at its highest point in the sky. Orbit. It's the path the object takes as it revolves around the other objects. So those are your 19 words for your vocabulary for astronomy. Next, we're going to talk about the Earth's shape. The Earth's shape is an oblate spheroid. The whole idea, if I'm looking at my circumferences, my polar circumference, which is going to connect North Pole to South Pole, let me quickly draw for you. My polar circumference in blue. My equatorial circumference, that's your equator. That one I'm going to do in green. So this is your equatorial, and this one's your polar. So if you look at the two of them, they're not that far off. The polar circumference is 40,007 kilometers, whereas the equatorial is 40,074 kilometers. From space, the Earth looks almost like a perfect sphere because they're so close together. The reason that your equatorial circumference is greater than your polar circumference is because the Earth is rotating. With that, with the Earth's rotation, what happens is, think of it, you had a beach ball. Take a beach ball and put a little pressure, put your hand on the top and the bottom of the beach ball. So I did this. Put a little pressure there. What you would notice is the top and the bottom of it get closer together, which causes the center to bulge slightly, or the equator to bulge just slightly. That has to do with the Earth's rotation. If I'm looking for Earth's smoothness, the Earth proportionally, even if I look at all the mountains and Mount Everest, proportionally looking at the size of the Earth is actually considered to be rather smooth. Next, going back to the shape, evidence of the Earth's shape. How do we know that the Earth is an oblate spheroid? First one is pictures from space. The second one is a disappearing ship. So if I have you, and here's my Earth, and here we were standing at a pier, and you're in a ship, and we're waving goodbye to you, as you travel over the horizon, the last thing that we see is the top of your mast. If it wasn't a curve, you would just get smaller, progressively smaller and smaller and smaller, which is not true. All right. Another reason is we see the sunlight before you actually see the sun. So if you guys actually go out early in the morning, you'll see the sky is brighter before you actually see the sun come over the horizon. Then the next one is a lunar eclipse. The Earth is casting a shadow on the moon. So here's the sun. Just like if you took a light without a shade on it and you projected it onto an object. The object on the side that the light is will be illuminated or lit. The opposite side will be dark. So the Earth being larger, is actually casting a a shadow on the moon. And we'll look at this later on when we talk about the moon. We can actually see as the moon comes in the Earth's shadow, you can see the curvature of our Earth. And lastly is the change in gravitational pull on the Earth. Now, if I am to weigh you at sea level, now it's got to be sea level, so remember, we only can have one variable. You will weigh slightly more at the poles at sea level than you would at the equator. That's because you are slightly closer to the center of gravity, or the center of the Earth, at the poles, so you weigh more, there's a greater pull, and you weigh slightly less at the equator because you're slightly further away from the center of gravity or the center of the Earth. All right, I want to talk to you about rotation. Rotation is, we said, when an object's gonna spin out on its axis. I'm gonna put a couple of videos for you guys to watch about the Foucault's pendulum and the Coriolis effect. All right, here's my version of Foucault's pendulum. I have my Lazy Susan. My pegs are my wooden blocks. So my keys are going to be the pendulum. So remember, Foucault's pendulum shows that the Earth is rotating. So if I start, my pendulum's right here. It's going to keep going. Notice my pendulum stays. It's only knocking these blocks down. They have to be 180 degrees from each other. Now, if the Earth wasn't rotating, the pendulum just stay here and wouldn't knock the other ones down. But because the Earth is rotating, so are the pegs that are on the Earth. So what you'll see is with each one, whoops, wasn't going fast enough. As I rotate, each peg is going to get knocked down. Hopefully that makes more sense now to the drawing that's in your notes. So the pegs up haven't been knocked down yet. The pegs down have been knocked down. Notice it's got to be 180 degrees apart. All right, so Coriolis effects, if I'm looking in the northern hemisphere, because of rotation, the object gets deflected to the right, and in the southern hemisphere, it gets deflected to the left. And like I said, I will be finding a video to insert for you for that one to make it a little more easy for you to understand. Okay, quick question. Do all parts of the Earth rotate at the same speed? Answer, no. That's because as it's rotating, if I think about it, the equator's got more distance to cover in the same amount of time than any other location. It's kind of like if I throw you guys out on the track. You all start, if I have you all start straight across the track at the same start point, I don't stagger you. So if I have you start at the same point and then I have to finish at that same line, the person that's running on the inside has less distance to cover than the person running on the outside. So if you have to finish, if you start at the same time and have to finish at the same time, the person running on the outside is going to run faster than the person running on the inside. Same concept with the Earth. Because the equator has got more distance to cover than any other latitude, it's got to rotate at a faster speed. So if I look at the equator, remember we talked about what the circumference was. 40,074 kilometers in approximately 24 hours. Doing the math, it is moving, or it is rotating on 1,669.75 kilometers every hour. If I come up to New York State around 42 degrees north, its circumference is 31,200 kilometers. In 24 hours, if I divide it by 24 hours, that's going 1,300 kilometers per hour. Now, if I look at the North Pole is a point. It doesn't have a circumference. So with that one, it's 0 kilometers in 24 hours? 0 kilometers per hour. Really important for you to know. How many degrees per hour does the Earth rotate? How we do this is a complete rotation is 360 degrees in approximately 24 hours. So 360 divided by 24 is 15 degrees per hour. So the Earth is rotating 15 degrees per hour.